Hey everyone, and welcome. Have you ever had a brilliant idea for a program, but then you hit a wall wondering how to actually translate that logic into code a computer can understand? Well, that is exactly what we're going to jump into today. We're going to explore how you can turn your ideas into a real C++ blueprint that a computer can build from. Let's get started.
Okay, so the best way to think about programming, especially in C++, is with this model right here. You are the architect. You're the one with the vision. You design the structure. You decide where the walls and doors go and how it all fits together. Your code, that's the super detailed blueprint. And the computer? Well, the computer's just the builder. It's incredibly fast and powerful, but it will only do exactly what that blueprint tells it to do. It's not going to guess, and it's not going to improvise.
Right, so that's the big question, isn't it? How do we get from this cool concept in our head to a precise, logical blueprint that our builder, the computer, can follow without a single mistake? Well, it all starts with the most basic materials. I mean, think about it. Before an architect can even think about designing a skyscraper, they have to understand their materials. Steel, concrete, glass. For us programmers, our materials are things like variables and figuring out how our program can actually talk to the outside world. So let's look at one of the most core concepts, and this slide makes it super simple. A variable is really just a container, like a labeled box for your data. You've got an int box that holds whole numbers, a double box for decimals, and a string box for text. By giving these boxes names we can remember, like age or username, we can store information and grab it whenever we need it. This is the raw material for our entire blueprint.
Now, a building with no doors or windows isn't very useful, is it? Our programs need a way to interact with the user. In C++, we do this with count and syn. Just think of count as the program speaking. It sends messages out to the screen. And syn is the program listening. It takes input in from the user's keyboard. Oh, and that NDL, you see? All that does is tell the computer to move to the next line, kind of like hitting the enter key. You put them together, and suddenly you're having a conversation.
Okay, so we've got our materials and we have a way to communicate. But a program that just runs in one straight line isn't very smart, is it? We need to create different paths, hallways and doors. We need our program to make decisions. This visual right here perfectly captures how programs manage their flow. It's just like a train coming up to a switch on the track. The program reaches a point where it has to choose a path. Does it go left or does it go right? And this choice isn't random. It's based on a very specific condition, a signal that tells the program exactly which track to take. So how does the program actually know which path to choose? It asks a question, but here's the key. It's a question that can only be answered with true or false. Computers don't really do maybe. Using these things called comparison operators, we can ask questions like, is the score greater than 90? Or is the password the user typed in equal to let me in? The answer to that simple true or false question is what determines everything that happens next. And here it is. This is the actual syntax, the language in the blueprint for making that decision. The if statement is our first question. That line, if score greater than or equal to 90, is just asking, hey, is the number in the score box 90 or higher? If the answer is true, boom, it runs the code for an A grade and then totally ignores the rest of this block. If it's false, it just moves on to the next question, the else if. And if none of those conditions are true, the else block at the end is our fallback, our default path. This structure is the very core of a program's intelligence. Great architects don't sit there and redraw the exact same window 100 times on a blueprint. They create a pattern, and then they just repeat it. In programming, we do the exact same thing. We absolutely do not want to write the same lines of code over and over again. We want to loop. And there are really two main situations where you need to repeat something. The first is when you know exactly how many times you need to do a task, like, say, count from 1 to 10. The second scenario is when you need to keep doing something until a certain condition changes, like maybe waiting for a user to finally enter the correct password. So let's check out the blueprints for these two ideas. Over on the left, you see the for loop. Think of it like a clip counter. It's perfect for when you know you need to do something exactly 5 times or 10 times or whatever. Now on the right, you've got the while loop. This is more like a security gate. It's going to keep asking for the password while the one you've entered is wrong. It just keeps repeating, potentially forever, until the correct condition is finally met. Now this shows an incredibly powerful and super common pattern. This while loop is basically the heartbeat of most interactive apps you use every single day. The program starts, it sets a little flag called done to false,
and then it just loops and loops, running all the main functions. It only breaks out of that loop when you, the user, do something that flips that done flag to true, like click and quit. Okay, let's take a breath. We have our materials, our variables. We have our communication tools, syn and cout. We've got our decision-making hallways with if and else, and our repetitive patterns with loops. Now it's time to do the really fun part, assemble them all into a cohesive blueprint for an actual application. The structure for a simple, interactive program is actually surprisingly straightforward. First, you start a main loop that just keeps the whole thing running. Inside that loop, you show the user a menu of their options. Then, you get their choice. And finally, you use that branching logic we talked about, our if and else statements, to figure out what to do based on their choice. That's it. And this diagram right here shows how those simple steps create a complete application lifecycle. The loop is the big circle that holds it all together, and inside you see that cycle: show a menu, get input, and then branch off to the correct piece of logic. This entire powerful structure is built from the exact pieces we've just been discussing. So the crucial takeaway here is that understanding these concepts is really just the first step. This quote hits the nail on the head. Like any craft, whether you're an architect or a carpenter, you only get good through practice. It's all about using these tools over and over again until drawing the blueprint becomes second nature. And you know what? In just the last few minutes, you have already climbed several rungs on this learning ladder. We started with simple input and output, then we moved up to making decisions with branching logic, and now you understand how to repeat actions with loops. You seriously have the foundational logic right now to build real interactive programs. So we've laid out the core logic and we've looked at the essential syntax. You now understand how an architect translates a vision into a blueprint. The tools are officially in your hands, so the only question left is, what are you going to build first?